All right. Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
And today we're going to get our acids and bases together.
God.
Ouch. Ouch, yeah.
Unit 17. This is the second to last unit, Mr. Kane.
We're doing
I'm
pretty
excited.
decent here. We're going right along.
And it looks like a big one.
There's actually a lot of stuff to do here, it looks like. But a lot of this stuff is related, so it's not going to be that much information.
Okay.
Okay, we start out by talking about definitions about acids and bases, and it turns out that there's two main definitions. Once we've got those definitions taken care of, we can talk about properties, and we can talk about the fact that acids and bases have what we call conjugates.
Yep.
Okay, they're kind of like brothers or sisters.
Yeah, okay.
We can identify strong and weak acids and bases, and that's going to be a memorization thing. Calculate and understand the Ka and the Kb.
And that's just mathematics.
And that's if you recognize that K, it's equilibrium. Equilibrium of acids and equilibrium of bases.
And water, apparently.
And there's a Kw, so there's an equilibrium of water also.
Okay.
Yeah, it turns out that water is not just water. We're going to calculate the concentrations of hydrogen ions, which has to do with the definition of acids, and calculate the concentration of hydroxide ions.
Yeah, which has to do with bases, yep.
We're going to talk about the pH scale and be able to describe it. We're going to be able to calculate different pHs for different solutions.
All right.
And we're going to be able to recognize a neutralization reaction, and ultimately, at the end of this unit, we should be able to take all of these concepts and wrap them up in what's called an acid-base titration. All right, so we might as well get straight into it.
Mr. Arrhenius, the Arrhenius definition of an acid and a base.
Right.
An acid.
All right, so he's a Swedish chemist in 1890. I don't think he come much more first than that, right? Sorry. But basically what Arrhenius said is that an acid is any substance that when added to water produces the hydronium ion.
Yep.
And the hydronium ion is basically water with an extra hydrogen.
Correct.
That's positive.
It's the hydrated hydrogen ion.
Hydrated hydrogen ion.
This guy was pretty smart because there's a couple other concepts named after him.
People with mustaches are usually smart.
Yeah, they are they? Okay.
So he also comes up with a definition of a base, right?
Right. Any substance that contains a hydroxide group and dissociates to produce a hydroxide ion in an aqueous solution, meaning in water, right?
And if I remember right, hydroxide is this, right?
Yep, that was one of the polyatomic ions, right?
Hydroxide. We've been using that all year long.
Yeah.
And there's some drawbacks to Arrhenius' definition. It's limited only to aqueous solutions.
Yeah, I noticed both of them for the hydrogen ion and the hydroxide ion. Both of them said in aqueous solutions.
Yeah, so they have to be in water solutions. So if it's in alcohol, you can't tell, or if it's in oil, you can't tell what the pH, whether it's an acid or a base. You also can't classify substances that sometimes act as acids and sometimes act as bases. And it doesn't explain why ammonia is a base. Ammonia is NH3.
Right.
It's the most famous base of all, but I don't see hydroxide ion anywhere there.
No, and isn't that a gas?
Yeah, it is a gas.
So you have a gas that's listed as a base, but that doesn't jive with the definition of Arrhenius base.
Right. That's okay because almost 30 years later, two gentlemen, one by the name of Bronsted and another by the name of Lowry, were working on figuring out how to better the Arrhenius definition. Okay, so a Danish chemist and a British chemist got, and they weren't actually getting together to work on this. They were working at the exact same time. All right, different parts of the world. And they proposed that an acid should be any species that can donate a proton. Species here meaning substance, right?
Right, any substance that can donate a proton. Wait, what's a proton?
What's a proton? Well, a proton, as far as we're concerned, if we want to talk about it being an element like an ion, the simplest thing is going to be hydrogen. It only has one proton, right? So if I take away the electron from a hydrogen atom, that's a proton.
Yep, and that's the symbol then, H+, yeah?
Okay, yeah. So so we come up with a symbol of H+ as being an acid, as being the proton. H+ as being the proton.
Okay, so an acid will donate an H+.
Sounds about right, yeah.
And a base apparently accepts.
A base, and by corollary, the base accepts the proton.
That looks pretty easy, and it covers all states of matter.
And we can see here, we could actually take a look at this. I've got HCl and I've got H2O, And if I take a look over here at what happened to those two things, it looks like HCl actually lost its hydrogen, right?
Donated it.
Donated it. So this is my acid right here, and some of us actually recognize that as
right.
hydrochloric acid.
So who did it donate to? Well, the only other reactant is water.
So water is my base because it accepted a hydrogen and became hydronium.
Yes, it accepted an extra hydrogen.
So we've got acids and we got bases.
Okay. Acid properties. They're sour tasting, corrosive to active metals.
So they'll actually dissolve active metals?
Yeah, pretty much. It's gonna, yep.
But non-active ones like gold, they won't.
Because if you recall, we did hydrochloric acid and zinc, and we got hydrogen gas.
We get hydrogen gas from that, yeah.
Turns blue litmus paper red.
So acids turn litmus red.
Correct.
Okay. I think I remember that from that demo we did earlier in the year with the equilibrium reaction, the MOM demo.
Yeah.
The acid turned
acidic was red.
It turned it red, right?
That's right.
Okay.
Conducts electricity because they're ions.
Because it forms ions. Yeah. Ions conduct electricity.
Reacts with bases, neutralization to form salt and water, which actually is what happens in your stomach, right? If you have a sick stomach, you got all that excess hydrochloric acid or hydrochloric acid in your stomach, you throw in an Alka-Seltzer, that's a base. That's what's going on in your stomach when you have indigestion, yeah?
Ah, okay.
Neutralization.
So you just mentioned a neutralization reaction.
Oh, look, and there it is.
We're going to do it anyhow.
I guess so.
All right. So you could take hydrochloric acid and something like sodium hydroxide. This isn't something that you would eat, would it?
Yeah, I would not. Alka-Seltzer is magnesium hydroxide. I would not advise trying to take sodium hydroxide pellets for a sick stomach.
Yeah, that will result in bad stuff happening.
That'll be more than a sick stomach your problem with, that's for sure.
Yeah, but so
we have an acid and a base there,
right? You got an acid, you got a base. The acid is right here because it's going to donate a proton, and here is the base. By donating the proton, the hydrogen actually comes over here with the hydroxide and forms water.
Right.
And the sodium winds up having to form up with chlorine, and we get sodium chloride. So just like you said, a neutralization reaction forms a water and a salt.
This looks suspiciously like a double replacement reaction also.
Yes, it does. You're right.
Yes, I remember that.
Are all neutralization reactions that we see going to look like
double replacement reactions? Yeah, pretty much.
Yeah. So here's a chart to write down, guys.
Yeah, you got to memorize these.
Okay, now, and here's the tip. Notice the list for weak acids.
Yeah, that's the one that's easier, isn't it?
Don't memorize any weak acids. Anything that's not on the list of strong acids is going to be a weak one.
Right.
As far as we're concerned for this class.
Yeah.
We'll make sure of that. So strong acids, hydrochloric, hydrobromic, hydroiodidic, nitric, sulfuric, and perchloric.
I say it iodic.
Did you say iodic?
Yeah.
I think different people say it differently.
Yeah, differently.
You say tomato?
I say tomato.
There you go. All right.
There are, let's see, 3 binaries, 3 oxys. Hey, one of them's a diprotic. Can you guess which one is diprotic?
Diprotic. Let's see, di meaning 2 and protic meaning protons. That's going to be one that has 2 protons.
Yep.
And we said already protons are represented by hydrogen. There's only one there that has 2 hydrogens.
Yep.
That's the sulfuric. Yeah. All right, and there's a reason why we have to memorize strong and weak, right?
Right. Strong acids dissociate 100%. They basically go to completion. They are all product favored, correct?
So a completion reaction, right?
Right.
They only go one way.
Right.
Weak acids, on the other hand, only dissociate partially. So they're kind of like an equilibrium reaction. They actually go back and forth.
We have a double-headed arrow.
And only a small fraction of the molecules actually get ionized at any given time. So only a small fraction of molecules are ionized at a given time. That means that I'm going to have small amounts of products, but large amounts of reactants.
Right, it's very reactant favored.
And very reactant favored. If this is a Ka, like an equilibrium reaction, like we said, then this means that I'm going to have a Ka. Means that I'm going to have less products and much more reactants.
Yep.
Right? Kind of like that.
So wait a second then. If there's a whole list of strong acids that all dissociate 100% and have a very large K, I'm assuming.
Only 6 of them.
Very product favored, 6 of them. How many other weak acids are there? Aren't they all going to be the same? What distinguishes weak acids from each other?
Oh, they have different Kas.
Oh, okay. All right. So we're going to, okay,
different acids are going to have different Kas.
So each weak acid has a different size Ka, which will determine how reactant favored that weak acid is.
Yeah.
Okay, got it.
Okay, and here's a visual of it, strong versus weak. You can notice here that the strong acids dissociate completely. I've got all ions here of hydrogen chloride.
There's actually no
hydrochloric acid.
compound of HCl in that left one.
Exactly.
They're all just the H and the Cl.
Right. Since this dissociated completely, if it hadn't dissociated completely, what I should be seeing is I should be seeing HCl. I should be seeing a complete acid particle, kind of like I see a complete HF particle over here.
Right.
But I don't see any of that in here. They're all dissociated.
Right. All you see is the hydrogen ions and the chloride ions. There is no compound in the solution.
So when they come in, they actually separate out into hydrogen and chloride ions.
They dissociate 100%.
100%.
Ionize 100%.
Very good.
And I notice for hydrofluoric acid, I see the compound in the solution.
Yeah, there it is, there it is, there it is, there it is.
So hydrofluoric acid is going to have the compound, the hydrogen ions, and the fluoride ions, and it's going to have a Ka.
Correct. This one will have a Ka that is less than 1.
Bases taste bitter.
Bitter, kind of like bittersweet chocolate?
Yes. Slippery, kind of like bleach.
Okay, or oils.
Oils in the skin.
Well, soap feels slippery, and it's a base.
Yes, that's very base. Turns litmus paper blue. Red litmus paper blue. Then.
I think I remember that also from the mom demo, right?
Yes.
Bases.
We went up to the
not just blue, but purple with the mom demo.
We went up to the purple, yeah.
But it goes towards the blue end of the spectrum.
Yep.
Okay. They conduct electricity, right?
Because they are strong ones also are ions.
Okay. And they often are crystalline solids when they're not dissolved.
Bases come as solids, and the acids come as aqueous solutions.
Okay, all right.
In the liquid form. Base that dissolves in water is called alkali.
Is that why they call them alkali metals?
Yep.
They dissolve in water.
Yep.
The strong and the weak bases, what you need to memorize. Don't bother memorizing the weak bases again. Just know that the strong bases are going to be the alkali metal hydroxides and the alkaline earth metal hydroxides.
So that's group 1A, with the exception of hydrogen.
So anything from group 1A or
and
anything
2A.
from 2A with a hydroxide. All right, so memorize these strong bases.
Yep, memorize them.
All right, so strong bases, like strong acids, dissociate completely. So this is a completion reaction when they dissolve in water.
Correct.
Yeah. And weak bases dissociate only partially, so it's an equilibrium reaction.
Yep.
And again, only a small fraction of them ionize, so this would be a Kb.
Yep.
And it's going to be less than 1 also, because I'm not going to get a lot of ions.
And you'll notice that each one of those is got the hydroxide in it, which is the base ion.
Oh, hey, check that out. You're right. It is. There's a hydroxide on both of the product sides.
Yep.
And that's what the base is.
Yes.
That's what Svant said.